Some of the biggest ideas in computing can feel a little bit like magic tricks. Well, today, we're going to pull back the curtain on one of the most powerful and honestly kind of mind-bending tools in the entire operating system toolkit. And to get us started, I want to show you a tiny little piece of code that seems to just break all the rules of logic. Okay, so check this out. It's a super simple program. It prints hello, then it calls this mysterious function named fork, and then it prints goodbye. Now, common sense tells you it should print hello once and goodbye once, right? But when you actually run it, you get hello once and goodbye twice. How in the world is that even possible? To solve this little puzzle, we've got to build a solid foundation first. So let's get two key terms straight in our heads. First off, we need to separate two ideas that sound similar but are totally different. On one hand, you have the program. Think of that like a recipe in a cookbook. It's just a set of instructions sitting there on the disk. Then you have the process. That's the chef actually using the recipe. It's a living, breathing, running instance of your program with its own memory and its own state. So a process is really just a program in action. And to keep track of all the different processes running on your computer, your web browser, your music player, all that stuff, the operating system gives each and every one a unique number. We call it a process ID, or just PID for short. All right, with that under our belts, let's get to the real heart of our mystery, this fork thing. This is the one function call that, well, it changes absolutely everything. This brings us to one of the wildest, most wonderful sentences in all of computer science. Fork is called once, but it returns twice. I mean, just let that sink in for a second. One function call goes in, two separate results come out. How does that even work? Well, here's the magic. Our single process is chugging along, and then bam, it hits the fork call. At that exact moment, the operating system creates an almost identical clone of that process. The original is now called the parent, and the new one is the child. And from that point on, they both just keep running from the very next line of code. And that's it. That's the answer to our puzzle. That's why goodbye got printed twice. Okay, so we have two identical processes now, both running the same code. But that brings up a new problem, right? How do they know who's who? Which one is the original parent and which one is the brand new child? The solution here is just beautifully elegant. It all comes down to what fork gives back, its return value. In the parent process, fork returns the unique process ID of its new child. But in the child process, fork returns 0. This one tiny difference is everything. It's like a secret handshake that lets each of them know exactly who they are. And that return value is the key that unlocks different paths in the code. See, the child process gets a 0 back from fork. So in our code, we can just write a little check that says, hey, if you got a 0, then you execute this block of code. And only the child process will ever take that path. And the parent? Well, it got a different value back, the child's ID, which is always a positive number. So it fails that is it 0 check. This means it takes the other path, the else block. Just by checking for that one simple difference, we get total control, and we can give the parent and the child completely different jobs to do. Now, you might be thinking, okay, that's a cool programming trick, but what's it actually for? Well, this isn't just some abstract concept. This whole cloning ability is the absolute backbone of one of the most powerful tools on your computer. I'm talking about your command line terminal, your shell. Literally every single command you type, whether you're listing files or running a huge program, it relies on this exact fork mechanism to do its job. Let's just walk through it real quick. The shell is just a process, sitting there waiting for your input. You type a command, say ls, and hit enter. Now the shell doesn't just become the ls program, because if it did, the shell would be gone. Instead, it calls fork to make a copy of itself. This new child process gets the job of running the ls command. Meanwhile, the parent, our original shell, just patiently waits for the child to finish up. Once it's done, the prompt comes right back, ready for whatever you want to do next. It's absolutely genius. Now, I know what some of you are probably thinking. Hang on, cloning an entire process? Doesn't that sound incredibly slow? Am I really duplicating all of that memory every single time I run a command? And that is a fantastic question. The answer is no, and it's thanks to this really clever optimization called copy on write. When fork happens, the operating system is actually pretty lazy. It doesn't copy all the memory right away. Instead, it just lets the parent and child share the same memory.
It only bothers to make a separate copy of a piece of memory at the very last second, the moment one of the processes tries to write to it or change it. It's incredibly efficient.
But, beyond all the clever performance tricks, the real beauty of Fork is just its design. The interface couldn't be simpler. It takes no arguments at all. It just does its one incredibly powerful job. This is a huge contrast to other systems that have these massively complex functions just to do the same thing.
So let's do a quick recap. A process is just a program in action. The fork call creates a nearly identical clone of that process. The secret sauce is the return value that lets the parent and child tell each other apart. And this whole mechanism is the fundamental magic behind the command line shell we use every day.
So, we've solved our puzzle. We now know how a program can literally clone itself, but that just leaves us with an even cooler question, doesn't it? How does that clone, which starts as an exact copy, totally transform itself into a completely different program, like LS? And how does the parent know exactly when its child is done with its work? Well, that's a story for our next explainer.